Hubble spent 35 years photographing the sky. In that time, it captured roughly 1 part in a million of the observable universe. NASA's new telescope will beat that in 63 days. The Nancy Grace Roman Space Telescope launches at the end of this month. It cost $4.3 billion. It has a field of view 100 times larger than Hubble's. It carries a 300-megapixel camera built to photograph not thousands of galaxies, not millions, but 2 billion. And it isn't built to photograph them just for the sake of photographs. It's built to solve the 2 biggest unsolved problems in all of physics. The first problem is one you've probably heard of, but probably don't appreciate the scale of. In 1998, 2 independent teams of astronomers set out to measure how fast the universe was slowing down. Gravity pulls matter together. The Big Bang sent everything flying apart. The question was simply, how much has gravity put the brakes on? They measured, and the universe wasn't slowing down, it was speeding up. The expansion of the universe is accelerating. Galaxies are flying away from each other faster and faster, not slower and slower. Something is pushing them apart. Something with enough power to overcome gravity at cosmological scales. We called it dark energy. We have no idea what it is. Here is what makes this terrifying. Dark energy makes up 68% of everything that exists. The ordinary matter, stars, planets, gas, dust, makes up less than 5%. The remaining 27% is dark matter, which we'll come back to. But 68% of the energy content of the universe is a force we discovered 28 years ago, cannot detect directly, cannot replicate in a lab, and do not have a theory for that actually works. We named it dark energy, the way you name a hole in the ground. It's where the explanation should be, and it isn't there yet. Roman is going to map it. The way Roman maps dark energy is by surveying the large-scale structure of the universe, the cosmic web of filaments and voids and galaxy clusters that spans billions of light-years. Dark energy's fingerprint is in the spacing of that web. As the universe expanded, dark energy pushed structure apart in ways that should show up in how galaxies cluster together across cosmic time. By photographing 2 billion galaxies spread across the history of the universe, some of them near, some of them so distant their light left before Earth existed, Roman will give us the most detailed map of cosmic structure ever assembled. That map will either confirm our current best model of dark energy or break it. Both outcomes would be enormous. The second problem is dark matter. Dark matter doesn't emit light. It doesn't interact with light. We can't see it, touch it, detect it with any instrument we've built. What we can do is watch how it bends gravity. Every mass in the universe curves space-time, and light follows those curves. Where dark matter concentrates, it acts like a lens, distorting and magnifying the appearance of galaxies behind it. This effect is called gravitational lensing. We've been using it for decades to map dark matter in crude sketches. Roman will do something categorically different. It will survey 2,000 square degrees of sky with a resolution comparable to Hubble's. That's a patch of sky 100 times wider than what Hubble could cover, at the same precision. The result will be the most detailed map of dark matter distribution ever created. The shape, the density, the clumping structure of something we cannot see and cannot touch, traced in the bent light of billions of galaxies. If the map matches our predictions, We confirm the standard cosmological model. If it doesn't match, we find out where our physics breaks. But Roman isn't only here for the two big unsolved problems. One of its instruments, a coronagraph, can block the light of individual stars well enough to directly photograph the planets orbiting them. We've been finding exoplanets for 30 years by watching for them to dim their stars or pull on them gravitationally. Roman will actually take pictures of some of them. There's another target, rogue planets. Planets that don't orbit any star. Planets that were ejected from their solar systems billions of years ago and have been drifting through the dark ever since. We think there may be more rogue planets in the galaxy than there are stars. Roman will detect some of them for the first time by watching for the brief brightening they cause as they pass in front of background stars, a signal that lasts hours, not years. The Milky Way may be full of homeless worlds. Roman will begin to count them. And then there's what Roman will find that we aren't looking for. Every major telescope in history has produced its most important discoveries by accident. Hubble was built to measure distances. It ended up revealing the universe's accelerating expansion. JWST was built to study the first galaxies. It found them forming 300 million years after the Big Bang, earlier than our models said was possible. Roman will survey more sky, in more detail, over a longer period of time than anything we've launched before. The catalog it creates will be searched by astronomers for decades. Things we haven't named yet, phenomena we don't have models for, objects we don't know exist. They're in that catalog. We just haven't read it yet. Here is what 2 billion galaxies look like in human terms. There are approximately 8 billion people on Earth. If you gave every human being a quarter of a galaxy, a small portion, just a slice, you would run out of people before you ran out of galaxies in Roman's survey. Each of those galaxies contains hundreds of billions of stars. Each star, potentially, orbited by worlds. Roman's map will be the largest and most detailed picture of reality that any civilization, anywhere in the universe, has ever attempted to make. It launches in 30 days. We built it because we don't understand 95% of what exists, and we finally have the instrument to start asking the right questions.